this new thing. I haven't tried giving face scan while I'm teaching. So I hope you can see a blurry image. That's all I can manage right now. So it's why I have given you, trying to provide you this face cam with this screen video, my computer screen video, so that I can relate with you guys. Okay, so this is the thermal stress, the topic thermal stress we'll be dealing today. Okay, so we are taking a topic each and every day on SOM, that is strength of material. I'll be also coming up with other topics like or subjects, design of machines, dynamics of machines, and also manufacturing technology, because my trade in my master's is that is manufacturing technology. So what is mean by thermal stress? So before going into the diagram, if we have to listen, then we have to write like things. Yeah. So what do you mean by thermal stress? So if I have to say, it is the stress due to temperature change. Okay. So if I have to define what do you mean by thermal stress, it is nothing but stress due to temperature change. Okay. So this is what a thermal stress means in very simple words. You can also say it like, you can also give a definition like stress induced in a body after heating or cooling. Yes, I have to write the word cooling also, because if you do heating, like most of the elements or materials go in the expansion form, and if you do the cooling, it gets contracted, right? You have also been studying compound cylinder, where you have used the cooling technique also, right? So in the first definition that we have written is the temperature change we are talking about. Means if you look into this cantilever beam into the left hand side, okay, this side, my side might be different in the face scan. Okay, so let me check which side. Yeah, this side for you, this side. Okay, this side. So if you see, you will know that. Let me put you can see the cantilever beam with this cross section, uniform cross section, the circular cross section we are thinking of. We are considering cantilever beam circular cross section area A, and total length is L. Suppose the initial temperature is Ti. Okay, whatever the temperature is, it is the Ti temperature. And what happens after heating? There is a change in temperature, okay, to Tf. That is the final temperature, initial temperature minus final temperature. So the final temperature minus initial temperature will give you that delta T. This delta T is nothing but, we are talking about the temperature change. And there are other properties also, that is E, or some of you might take it as Y, that is the Young's modulus. Okay, so Young's modulus, as we all know, for us it will be Newton per mm square. And there is this delta T we have talked about. So it will be either in degree Celsius or Kelvin. Okay, we will see whatever in that numerical or numerical problem is given, we have to consider. And there is this this one, yeah, alpha means thermal expansion coefficient. Okay, thermal expansion coefficient, these are the material property. Okay, this Young's modulus and E are the property of the material. Whatever material you are using, that is the property. Okay, thermal expansion. So what do you mean by thermal expansion? Okay, see, at certain temperature there is a body, and if you change the temperature by cooling or heating, it will expand or contract according to nature of the material, and each material has its own thermal expansion coefficient. Okay, so its unit is per degree Celsius or Kelvin, per Kelvin. Okay, so according to the definition, what is happening that if you give means if you are heating or cooling a body, there will be stress induced in the body, and that stress is called the thermal stress. So there is this three cases, okay, of thermal stress. First one is the free expansion. Okay, free expansion. Second one, completely restricted. We'll talk each one, we'll discuss each one. And the last one, I hope you're getting, the first one is the free expansion, second one is the completely restricted, and third one is the partially restricted. See, the stress in this cantilever beam will not induce until you stop this expansion. See, it is increasing in this direction. though we are taking a longitudinal direction. So for this case sake, just think that this is increasing, right? From this line to this line, it is increasing towards the right of the screen. Okay, you can see that, right? So what is happening? But if you stop this change in length, means it is changing from L to L plus delta L, is it not? Okay. So if you don't allow this delta L to happen, what will happen? See, if I show you an example, suppose there is this your cantilever beam, okay, and it is trying to increase in this direction, okay, after the change in temperature or heating, let's say. And what is happening in that case? If you give a support like this in here, so you are restricting the expansion. Only in this case, your thermal stress, because the change in length is happening due to the change of temperature, your thermal stress will be induced. Otherwise, it won't induce. So, in case of free expansion, actually there will be no thermal stress. Let's see why and how. Okay, first one, your free expansion. Let me draw the figure. Here, this is the L. Okay. See, there is no support at the right hand side of the beam, right? It is allowed freely, right? Free expansion is allowed. Okay. So this is delta L. We are allowing the complete change in length due to the change in temperature. Okay, please mind that in free expansion we are doing uniform heating. Means we are heating in at the same amount of heating is done on all the parts of the beam, not only one side or one end. It is a uniform heating. Okay, so after doing uniform heating, you are allowing the complete change in length. Means your L is changing from L to L plus delta L, and your temperature from initial temperature Ti, it is changing to Tf. And it can be any kind of material, so E and alpha will always be constant for that material. So what is happening now? Your delta L, which is actually free for free expansion, since we are taking it for uniform heating, it can be also for uniform cooling also. So for heating, we will use the plus sign if we have to show. Okay, otherwise it is not needed. And for cooling, we have to show it the negative sign. For delta L, it will be what? It will be your L into alpha into delta T. Are you getting my point? See, delta L and L has the same unit, and alpha and delta T has the reciprocal unit. So alpha and delta L will be cancelling out both of its unit. So your delta L is equal to L into alpha into delta T. So by dimension analysis, we are right. So what is happening in that case? Okay, since you are not restricting, if you see in this diagram, it is going in this direction, right? It is going in this direction, and there is no stopping. There is no support at the right. It is not restricting. There is a free expansion. It is expanding the amount it wants, right? It is expanding the amount it wants. Okay. So now the thing is that the molecules of this beam, this cantilever beams, is not restricted. It is allowed to get expanded. So in this case, there will be no stress induced. I repeat again, there will be no stress induced. So your thermal stress delta Th will be 0 for free expansion. Okay. See, free expansion can be either due to uniform heating or uniform cooling. In uniform heating, it will try to expand, and in uniform cooling, it will try to contract. But if you are not stopping it, if the molecules of the beams are not getting restricted at any sense or any case, then the stress will not be induced. In this case, I am talking about the thermal stress, because we are dealing with the temperature. Okay, so the thermal stress will be 0 for uniform for free expansion. Okay, you have to remember this. Okay, so questions might come like that there is a cantilever beam with so and so property, with length this, with Young modulus, with thermal coefficient this, and it is free. It is allowed for free expansion. Okay, so you have to write that there will be no stress induced, no thermal stress induced. Okay, let's go into the second one, that is the completely restricted. Now the concept will be more clear. Okay, now the second topic is completely restricted. Okay, so what we have to do, see, we are changing the diagram bit. We are taking the cantilever beam. and we are putting a support, a fixed support in the right hand side. So now what is happening? There is this delta L, sorry, there is this length L of the beam, and the cross section is same as before, that is A, and its property E and alpha are constant. Now what is happening? You have put a fixed support into the right side. So whatever delta L is trying to get, okay, it is not possible for the beam to happen because we are not allowing the free expansion. You have completely restricted. You are not even allowing a slight change in L. So your L would not become, I'm using the cross sign, plus delta L. So you are doing what? You are restricting it. So for this reason, what will happen? Your thermal stress will be induced. Are you getting my point? Your thermal stress, because you are giving a stoppage or a restriction to the molecules of the beam. Okay, so your thermal stress will be induced. So your del L, okay, del L for fully restricted. Let me write it again. For fully restricted will be what? The formula remains the same. That is L into alpha into delta T. Delta T is a change in length. So if you take it as del L fully, let me write it as res. Okay, I'm writing in short form. I'm taking the L here. It will be alpha into delta T. So change in length by total length will give you the strain. In this case, this strain will be known as thermal strains. That is epsilon TH. Okay, it is nothing but thermal strain. So it will be sigma into, I'm just mentioning, okay, don't take it as a the bracket I have written thermal strain, it is not multiplied, okay, I'm just letting you know that this is thermal strain into delta T. Okay, so what you have got epsilon TH equal to alpha into delta T, and you know, if you from the stress Hooke's law, your stress is directly proportional to the strain, and E comes out as a proportionality constant to becomes like this. So if you multiply Young's modulus to your strain, it will give you the particular stress. So your thermal stress delta TH will be epsilon. So you have ended it here. Now you can write it as delta TH equal to epsilon TH into E, your Young's modulus. Okay, and along with that, you have to now put the value of this thing alpha into delta T here. Okay, so your delta sigma TH equal to alpha into delta T into E. So whatever the value you have got, or the expression you got, it means that it is the thermal stress that is induced. In this case, since it's completely restricted, obviously there will be a stress induced due to the change in temperature, change in length, but you have not allowed the change in length, so there will be a stress induced, and that stress is alpha into delta T into E. Okay, and again I'm saying this sigma that you have got, that is the stress you are indicating. It can be for heating, also for cooling. Okay, please mind that. Let's move on to the third case, that is partially restricted. Means in this case, you are neither allowing full expansion and you are neither allowing total stoppage of the expansion. Okay, you are allowing slight expansion, so that's why partially restricted. I'll show you the figure in a bit. Partially restricted. So let me first draw the cantilever beam. It can move up to here. Okay, that is the distance or the length of the beam. The uniform cross section is A, and E or alpha are the property of the material, and that is the delta L. Okay, but in this case, what is happening? You are putting a fixed support in here, and this distance is X. So you are not allowing total expansion, that is the delta L, but you are allowing slight expansion. So what will happen? Your del L partially restricted, PR is partially restricted, I'm writing in short form, will be L into alpha into delta T minus X. Do mind this, L into alpha into delta T is nothing but the length. So I'm deducting length from a length. Okay, so you might think, how can you deduct X from it? Because it is entirely a length. Because at the left hand side of the equation, it is the length that we are taking. Okay, so dimensionally we are correct. As a mechanical engineer or an engineer, you have to be very careful about the equations, whether you are dimensionally correct or not. Okay, so the L into alpha into delta T minus X, that is your change in length. What will happen in that case? So if you try to find out sigma TH. So sigma TH, that is thermal stress, will be equal to epsilon TH into E, your Young's modulus, right? So what will happen, since you have allowed expansion of X, not total del L, so there will slight, it's actually mixed case of free expansion also completely restricted. So since it's not completely restricted and since it is not completely freely expanded, so in between you have to think like that. So what will happen now? We can do it like it. See, thermal stress will be defined by this thing, right? That is sigma TH will be, okay, let me keep that aside and write it like that. Delta L P are completely restricted. I'm taking the initial equation minus X. Let me divide it by L to the both side. Okay. So what will happen? In the left side, you can written it as thermal strain equal to L into delta T minus X whole divided by L. Okay. So now you have got the thermal strain. It is nothing but thermal strain. Okay. And now the thermal stress, we have written the expression earlier, sigma TH equal to L epsilon TH into your E, that is Young's modulus. So your sigma TH will be L into alpha into delta T minus whole by L into E. Okay, that will give you the thermal stress for the partially restricted. See, this thermal stress can be also due to cooling and also due to heating. Please mind that. So in the both three cases, you can pause the video, you can check the video, you can stop and take the notes. And if you have any doubts, do let me know in the comments. Before I do end up the video, you have to know one thing. See, if you do heating, it will, what will happen in the beam? In the beam or in the object, it will try to expand. So if you stop or try to stop the expansion, what will happen? Stress will be induced. Okay, stress will. So how do you? What type of stress it is? Thermal stress. Okay, I'm repeating again. Please wait. Okay, so if you do the heating, there will be expansion in the object or the beam, and stress will be induced. That will be thermal stress. Okay, this stress will only be induced if you try to stop the expansion. It can be fully expansion or a half expansion, but if you try to stop the expansion, there will be stress induced, and the this thermal stress will be compressive in nature. Are you getting my point? Because you are trying to push the object in the fully restricted case. Do you remember? See, it is trying to increase, but you have fully restricted it. Since it is also in fixed support, it cannot have the increase in length or the change in length. For that case, it is in the complete restriction that this stress, which is the thermal stress, will be compressive in nature. Now, in the same thing, in the same beam fixed at both ends, if you do cooling, what will happen? There will be tensile, because the thermal stress that is developed, that will be tensile in nature, because it will shrink in size or in length. So the fixed support will try to pull it off. So there will be, in case of cooling, it will be a tensile stress. Okay, so that much you have to remember regarding the thermal stress. In the next video, we will be solving two numericals for it. And till then, do subscribe to the channel because it will motivate you. Thank you so much. Bye bye.